Hello, let's have a look at the structure. I've been asked to have a look at the solvent sphere and see what's going on. So there is some issue with this order, and that's what I see when I open this in OLX2. Well, first off, the data look fairly good. 11.6 I over sigma. Our index is excellent. It's been possibly cut at 0.83. Let's have a look whether there's an omit command in there that we might not want. No, it's all there. So it was only this really only diffracted to 0.83. Let's look at the info and reflection statistics and get the I over sigma plot, because that's very helpful to see. So yeah, there was really nothing left. So sensibly the data was not, it's included even though this is clearly below the sort of acceptable limit. So really this is not a very high resolution data set, but let's keep this in mind for later, see what happens. Okay, first of all, the res file or the ins file, the res file I've got here doesn't have any information about the refinement in it, so we need to do one cycle of refinement or refine in OLX2. We're going to use shell XL, that's fine, and 10 cycles, well that's overkill, we only really need 4, and hit refine. So we should get a display of the what happens here. So yeah, a lot of things are moving. Goodness of fit is not very good. There's quite a big peak, 3.3, and where does it sit? It sits here. So F4 to toggle the let's go F2 to toggle the white background. So there's a big peak here. There's quite some peaks in here. We can also look at the density peaks. So these ones here are probably real. This one is almost certainly a water molecule, name O. So I just typed this down the bottom here, name O. I should maybe make this font a little bit bigger, draw style, seam properties, and I edit the font and make this 20 so it can be seen a little bit better. Okay, so this font is bigger and there's a few lines too many, so I go lines 3. Just want to see something happens. We're not interested in the feedback at the moment. Right, okay, so we made one extra oxygen and we've got these chlorines which look really rather big. The ADPs of this chlorine look healthy and this is much too big. The next thing we want to look at is the formula. So at the moment it's Cl4Cu2, so that's 2 chlorines per 1 copper, which makes sense. That's 2+, so we want that ratio, but there's also a green thing, so that tells us that formula that's currently assumed here is not what's on the screen. So if we click that green button, then now we see what we've currently got is actually 3 chlorines per 1 copper. So that's too many chlorines. So that's also makes sense in terms of these chlorines being a little bit too big. So let's make them half occupied. So I do this by typing fix occu 0.5. And let's refine. Control R is what I hit on the keyboard. The R factor went down per 2%, so that's good. Could have been that oxygen, of course. And the chlorines now all together look slightly healthier. Let's make this all anisotropic. So this water is also anisotropic. It's not a very healthy water. And now I guess the problems begin. So that water molecule looks like it's taking up too much room. It is really less occupied than suggested by this model. We've still got some peaks left over. Let's just take those biggest peaks and name them oxygen, and straight away set the occupancy to 1/2. We've got this on the command line, so I use the up key, fix occu 0.5, and Control R. Let's refine this and make it anisotropic again, so we can just type anis and refine. So now the R factor is dropping 7.91. That's looking a little bit healthier, but this one isn't looking very good. So it's still a fully occupied water. Let's try making this half occupancy as well. Control R. And the R factor is dropping some more, so that wasn't such a bad guess. So I suspect right now, if you click on this, it should put everything together. So we've got this sort of arrangement here. What we've got is we've got some chlorines. We can move this over here. What I do, I select this, go to View and then hide the symmetry generation, symmetry tools, move near. So I select this, and the next one I'm going to click now is going to be moved near this one. So we've got all this solvent or solvent sphere stuff in here, and the R factor is clearly a lot better than it was. So we're getting somewhere. The goodness of fit is also adjusting. Let's go back to work and look at the refinement. So this R weighting scheme is slowly settling. The shift, let's refine again and see what we get. Okay, is it settling? Well, it's moving about a little bit. That's not so good. Let's see what's actually moved. Yeah, it's all of them. I suspect that's not actually right. Add the hydrogens to these water molecules. And that obviously have to be fixed eventually, but at least they're in, so that means the formula will be reflected correctly. Didn't add it to this water, so let's just try again. Add. It refuses to add them. Control G to grow things, just to see what else is going on. So there is stuff going on here that is not looking too good. So these two oxygens are symmetry equivalents. That's why, one of the reasons why they are quite elongated. Let's click on this again, and let's look at the electron density map. That is usually quite a telling thing. So there's obviously something going on. So there's almost like a channel of electron density down here where there is water disordered, and these chlorines at half occupancy actually look fairly reasonable. So my inclination would be to say this is probably not so far from the truth. So we go fuse to go back to just the asymmetric unit, and let's try this button again. So we now got a formula of CuCl2. We've got a sort of non-integral oxygen count. That's because we put in half occupied oxygens here. So obviously a little bit of work is required here, but I suspect with a bit of perseverance and a bit more modeling, this may well result in an acceptable structure. It's never really ideal because the R factor is really rather high. With an R int of 4%, we expect the structure to be about 4%, and really it's not very clear cut. The R factor is just a little bit too high. So let's look at some bad reflections. So absorption correction hasn't been done properly. There's some outliers in here. They're all lower angle reflections, so possibly they're under the beam stop. Let's just omit them and Control R to refine, and we will hopefully find the R factor drops a little bit. We've still got quite a big shift. It's this one here now. You see, one of the problems is a half-occupied chlorine looks almost the same to the diffraction image as a water molecule would. It's about the same number of electrons, so it's hard to see. So there could well be a disorder that in this position there's also a water and less chlorine, and there's a bit of chlorine in here and the water. Looks to me like this is a channel. Let's grow this, or let's pack this. Let's pack the cell and see how all of this lies in the cell, and it's quite clear. Yeah, these are sort of, you know, in big layers. These channels of this in the solvation sphere. So let's grow it. So we see more, and then we can also go grow minus W, which employs all the symmetry elements that have all these operators that haven't been employed yet. We can align it with Matra 1 that aligns it along the A-axis, Matra 2. There we go. So this channel is really sort of filled with these chloride water molecules, and I suspect that's causing one of the problems. There's nothing holding it in place. Not ideal. Go back to fuse. Things are still wobbling. Let's try to add the hydrogens again to this. It still doesn't like adding hydrogens to this. We can right click on this and see what's going on. Bang, explore, and there's a lot of stuff going on this water molecule, and it just doesn't know where to place these hydrogen atoms. This is all we're growing, the environment of this. It's sitting in there. There's no obvious directions where these hydrogens should be placed, and that's why OLX2 refuses to place them. And at the presence of these peaks there also is quite clear cut that it just doesn't know where it's going here. So one of the solutions would of course be to select all these water molecules. We can do this by going cell $O, and then we go kill $H. That deletes all the hydrogens of everything that's currently selected. The problem with that is, I must have selected those ones as well. So we select those and go H add. So that adds the hydrogens back to the main molecule. The problem with this is that the formula now will of course be out of sync, because we really have water molecules that do have hydrogens. So the final formula must contain these hydrogens, even though it may, like in this case, not really possible to model them. In fact, I actually think it would be possible to model them, but for the purpose of this particular little video, that's not really what I want to go into right now. This now will hopefully result in a stable refinement. It is stopping somewhere here. You may just refine a few more times and hope that this system will settle. If it really doesn't settle, we just need a few more cycles right now, but I think it's coming to the point where it's settled. And I think, while this is not an ideal structure, and while I think there are some real issues with that, it's probably close to the reality of what's going on here. Okay, I hope this was helpful, and thank you for using OLX2.